In this lesson, we will work through an application of polynomial functions. The problem. An open box with no top is to be constructed from an 8.5 inch by 11 inch piece of cardstock by cutting equal-sized squares from each corner and folding up the sides. What is the maximum volume of the box? What are the dimensions that result in maximum volume? The objective function and constraints. Here's our piece of cardstock, and if we cut out squares from the corner, let's say each of these squares is x inches by x inches, and fold up the sides here, I will have a box that looks something like this. Notice that if we fold up the sides, our height of our box will be x inches. We don't know what the length is, so let's call that L, and let's call the width W. Okay, well, my objective function is going to be the volume function, because volume is what I'm trying to maximize here. My volume for my box will equal length, which is L, times width, which is W, times height, which is X. Okay, and I will use some constraints here to determine how I can get my volume function all in terms of X. Okay, my cardstock paper is 8.5 inches by 11 inches. When I fold up the corners to create my box, the length of my box is going to be 11 inches minus 2x. And the width will be 8.5 inches minus 2x. These are my constraints for width and length. Okay, if I plug in those constraints into the volume function, I will have volume is equal to the length, 11 minus 2x, times the width, 8.5 minus 2x, times x. I'll simplify my volume function by expanding, and we'll have volume is equal to 4x cubed minus 39x squared plus 93.5x. What is the maximum volume of the box? Let's look at our volume function, and we see that the highest power of this polynomial is 3. So we have a polynomial of degree 3. If our polynomial was degree 2, we would have a quadratic function, and we could find the vertex of the parabola, and we'd know what our maximum volume was that way. With a polynomial of degree higher than 2, we need a little extra help, such as a graphing calculator or Wolfram alpha, which I've used here. I typed in maximum V equals and my volume function into Wolfram alpha, and it told me that the maximum volume is approximately equal to 66.1482. So I will just say my maximum volume here is approximately 66.15 cubic inches. What are the dimensions that result in the maximum volume? Well, I also found from Wolfram alpha that for the maximum volume, x is approximately equal to 1.58542. The width of my box is 8.5 minus 2x. If I plug in 1.58542 for x in my width equation here, I end up with a width of approximately 5.33 inches. And if I plug in this x value into the length of 11 minus 2x, I find that my length is approximately equal to 7.83 inches. Next, let's find the domain. Well, I'm trying to find the x values that will be part of the possibilities for creating a box. And I start with knowing that my width, which is 8.5 minus 2x, has to be greater than 0 in order to create this box. I can't have a width of 0 or a width that's less than 0. Well, if that's the case, then I know that negative 2x will be greater than negative 8.5 by subtracting 8.5 from each side, and then dividing through by negative 2 gives me x being less than 4.25 inches. Need to flip that inequality sign. Okay, the length, which is equal to 11 minus 2x, must also be greater than 0. I'll subtract 11 from each side. Flip the inequality sign when I divide through by negative 2, and I'll find that x needs to be less than 5.5 inches. Additionally, x will have to be greater than 0 in order to have a box at all. We need to have some height to our box. So if I take the intersection of these three restrictions on x, I'll find that 0 is less than x is less than 4.25 inches. This would be the domain for this function. Try on your own. An open box with no top is to be constructed from a 2 by 3 foot piece of cardboard by cutting equal sized squares from each corner and folding up the sides. What is the maximum volume of the box?